Hi everyone, my name is Anya, and today on Math and Science Concepts, I will be talking about the periodic table. Make sure to like, share, and subscribe, and hit that notifications bell before we begin. So let us begin. The periodic table we are all familiar with was formulated by Russian chemist Dmitry Mendeleev in 1869. The ideas behind it began formulating 200 years earlier, and almost another 150 years later, the template it created is used in various designs, from artistic visions to organizing candy. Basically, the table groups elements together based on similar and increasing or decreasing properties or characteristics, and allows scientists to predict where the elements we have not yet discovered will fit in once we do. But Mendeleev's table did more than just foretell the existence of new elements. It validated the then controversial belief in the reality of atoms. It hinted at the existence of subatomic structure and anticipated the mathematical apparatus underlying the rules governing matter that eventually revealed itself in quantum theory. His table finished the transformation of chemical science from the medieval magical mysticism of alchemy to the realm of modern scientific rigor. The periodic table symbolizes also not merely the constituents of matter, but the logical cogency and principled rationality of all science. And there are many ways to arrange the periodic table, like on this slide here. Theodore Benfey's arrangement is an example of a continuous spiral table, as you can see the spiral here. First published in 1964, it explicitly showed the location of lanthanides and actinides in the periodic table. The elements form a two-dimensional spiral, starting from hydrogen and spiraling out and folding their way around the two peninsulas, the transition metals, and lanthanides and actinides. A superactinide peninsula is already in place. In a book by Stuart P. J., Amateurs and Professionals in Chemistry, The Case of the Periodic System, on spiral periodic tables, he writes, Mendeleev steadfastly refused to depict the system as such. His objection was that he could not express this function mathematically. Furthermore, the periodic table has evolved to reflect over 150 years of scientific development and understanding in chemistry and physics. And currently, the periodic table of elements looks like this. So here is the periodic table, and you can see the many different groups that the elements are categorized into below the table. The table consists of the alkali metals, the metalloids, the actinides, the alkaline earth metals, reactive nonmetals, elements with unknown properties, transition metals, noble gases, post-transition metals, and the lanthanides. The creator of the periodic table, Dmitry Mendeleev, in 1869 began collecting and sorting known properties of elements, like he was playing a game while traveling by train. He noticed that there were groups of elements that exhibited similar properties, but he also noticed that there were plenty of exceptions to the emerging patterns. Incredibly, instead of giving up, he tried altering the measured property values to better fit the patterns. He also predicted that certain elements must exist, which at the time didn't. Again, in an effort to get the patterns in his game to work out. So why do we arrange elements in a table? To help scientists and students understand the relationships between elements and their properties, as well as the table's organization reveals patterns in the element's properties, making it easier to study, compare, and contrast related elements. This information can also help predict the properties of elements and their compounds, as well as the existence of new elements. So moving on, does the periodic table change? The periodic table as we know it today is managed by the International Union of Pure and Applied Chemistry, or IUPAC. While much of what is in the periodic table is stable and unlikely to change, the IUPAC organization is responsible for deciding what needs to be changed and what doesn't. They have created criteria for what constitutes the discovery of a new element. In addition, any new element must be assigned a temporary name and symbol, and if validated, given an official name. Such was the case when IUPAC recently reviewed elements 113, 115, 117, 118, and decided to give them official names and symbols. Atomic weights found within a periodic table one might think are constant. The truth is, atomic weights have changed as a function of time. Since 1899, the IUPAC Commission on Isotopic Abundances and Atomic Weights, or CIAAW, has been evaluating atomic weights and abundances. For example, carbon had an atomic weight of 12.00 in 1902, but today it is 12.0096 or 12.0116. Times sure have changed as the source of the sample will determine the value. Moving on, we will be talking about periodic law. So the periodic law. When Mendeleev put his periodic table together, nobody knew about the existence of the nucleus. It was not until 1911 that Rutherford conducted his gold foil experiment that demonstrated the presence of the nucleus in the atom. Just 2 years later, in 1913, English physicist Henry Moseley examined X-ray spectra of a number of chemical elements. He would shoot X-rays through crystals of the element and study the wavelengths of the radiation that he detected. Moseley found that there was a relationship between wavelength and atomic number. His results led to the definition of atomic number as the number of protons contained in the nucleus of each atom. He then realized that the elements of the periodic table should be arranged in order of increasing atomic number rather than increasing atomic mass. When ordered by atomic number, the discrepancies within Mendeleev's table disappeared. Tellurium has an atomic number of 52, while iodine has an atomic number of 53. So even though tellurium does indeed have a greater atomic mass than iodine, it is properly placed before iodine in the periodic table. Mendeleev and Moseley are credited with being most responsible for the modern periodic table and periodic law. When elements are arranged in order of increasing atomic number, there is a periodic repetition of their chemical and physical properties. The result is the periodic table as we know it today. Each new horizontal row of the periodic table corresponds to the beginning of a new period, because a new principal energy level is being filled with electrons. Elements with similar chemical properties appear at regular intervals within the vertical columns called groups. The periodic table of elements is shown here. There are currently 118 elements on the periodic table. If that sounds like a lot more than you thought, it is probably because elements get added all the time. In fact, it was only in December of 2015 that the 4 latest elements were accepted by the International Union of Pure and Applied Chemistry, or IUPAC. Numbers 113, 115, 117, and 118. Their names ununtrium, ununpentium, ununseptium, and ununoctium. I kid you not. Each one of these names means its number in the Latin language. They are nothing but temporary placeholders until proper names have been devised for these elements. It's usually names inspired by scientists or science institutes, like Einsteinium, named after Albert Einstein, or Californium, with atomic number 98, which was named after the state where it was first created, the University of California Radiation Laboratory in Berkeley, 1950. Up to the year 1500, only 9 elements were known, 8 of which had been known since ancient times. The human body is mostly made out of 10 of these 118 elements, with tiny traces of another 10. The rest of them are altogether different stories. Some cannot even be found in nature, although it has been proven that they once existed in nature. It all gets very complicated, but it is the format and creation of this table that has led many much more fun periodic tables, from alternative arrangements of the original to periodic table inspired miscellany, which was only to be expected. After all, such a useful and iconic tool can only breed imitations, spin-offs, and parodies. So, the key to understanding the periodic table is the layout. How do I read the periodic table? The table is comprised of 7 rows, called periods, and 18 columns, called groups or families. Some tables, like ours from before, also includes colors to help identify groups that cross rows and columns. The colored areas of our table break up the elements into groups of alkali metals, alkaline earth metals, lanthanides and actinides, transition and post-transition metals, metalloids, nonmetals, halogens, and noble gases. We go in depth on each of these questions or these groups in the next slide. Located on the right above the English name for each element is the largest letters, representing its chemical abbreviation. The largest number is the element's atomic number. Other information in the box includes the element's electron configuration, electronegativity, oxidation states, and its first ionization energy. measured in kilojoules per mole. You can see this in the depiction here. An element, simply put, is a fundamental unit of matter that cannot easily be broken down. It consists of a specific number of protons and variable numbers of neutrons and electrons. All of matter is made of these 118 elements, combined in various ratios and kept in different states, like solids, liquids, and gases. Depending on where you are in the universe, some may be more prevalent than others. Here on Earth, elements like oxygen and hydrogen are common, but technetium, nihonium, and rhodium are rare. Super rare. So, on the periodic table, there is a family of 8 elements known as the precious metals or rare metals, including elements 44 through 47, like silver, and 76 through 79, like gold. These metals are considered to be both very rare and of a very high value. Of those, the two most rare metals are rhodium and osmium. This means that they are not commonly found naturally on Earth or within the universe. Some elements, like aluminum and iron, are abundant in the Earth's crust, while others are extremely rare. However, producing even the most common elements requires enormous energy and manpower. The alkali metal family includes the 6 elements in the first column of the periodic table, from lithium down to francium. These metals all contain one valence electron, meaning they form cations and react readily with water. These elements form the ionic bonds known as salts. Hydrogen may be mistakenly placed into this family, but it does not contain any of the family traits. The alkali metals are all shiny, soft, and highly reactive metals at standard temperature and pressure, and readily lose their outermost electron to form cations with a charge +1. They can all be cut easily with a knife due to their softness, exposing a shiny surface that tarnishes rapidly in air due to oxidation by atmospheric moisture and oxygen, and in the case of lithium, nitrogen. Because of their high reactivity, they must be stored under oil to prevent reaction with air, and are found naturally only in salts and never as the free element. What are alkali metals? Sodium is the most abundant, followed by potassium, lithium, rubidium, cesium, and finally francium, which is very rare due to its extremely high radioactivity. The alkali earth metals represent the second column on the periodic table. Its 6 elements extend from beryllium to radium. These metals are named for forming basic solutions when put in water. They tend to form cations with a positive +2 charge and bond ionically. What are alkaline earth metals? Beryllium, magnesium, calcium, strontium, barium, and radium, occupying group 2A of the periodic table, are alkaline earth metals. The lanthanide and actinide refer to the 2 families of most radioactive metals in an offshoot of the periodic table. Usually, they are shown as 2 rows on a separate section. The top row houses lanthanides, which are elements 57 through 70, The bottom row contains actinides, elements 89 through 103. These metals have very unique properties, owing to their f orbital arrangements and unstable nuclei. As an example, uranium, a common nuclear fusion source, is part of this group. What are lanthanides? Lanthanides consist of lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thallium, ytterbium, and lutetium. One of the most important properties of actinides are that they are radioactive in nature. The elements in this series are highly radioactive. Radioactive refers to the breaking down of the nucleus into smaller particles. The smaller particles are alpha particles, beta particles, as well as gamma particles. The elements in the actinide series release a large amount of energy on radioactive decay. The elements of actinides are used as nuclear reactors and in nuclear weapons. Thallium, one of the scarcest lanthanides, has an abundance in the Earth's crust of 0.2 parts per million and is more abundant than arsenic or mercury. The most abundant is cerium, which is more abundant than tin. Promethium, which is radioactive, is found only in trace amounts in uranium ores. So what are actinides? Actinides contain actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. So, moving on. Continuing our questionnaire of the different groups in the periodic table. The transition metals include 34 metals in the middle of the periodic table. These metals are named this way as they can take on many different charges due to their valence electrons being in the d orbitals. As a result, these metals tend to have a wide variety of colors and properties. What are transition metals and post-transition metals? Iron, platinum, molybdenum, nickel, palladium, zinc, and copper are transition metals. The post-transition metals are those metals that come after the transition metals, but before the noble gases, within a row. There are only 8 of them, but they can take on some very unique properties, charges, and colors. The post-transition metals are aluminum, tin, lead, and many others. They are post-transition metals. A metal is a material that, when polished or fractured, shows a lustrous appearance and conducts electricity and heat relatively well. These properties are all associated with having electrons available at the Fermi level, as against non-metallic metals which do not. Metals are typically ductile, which means they can be drawn into wires, and they are also generally malleable, meaning they can be hammered into thin sheets. By the way, the highest energy level that an electron can occupy at the absolute zero temperature is known as the Fermi level. The Fermi level lies between the valence band and the conduction band. It is at absolute zero temperature. The electrons are all in the lowest energy state. Metalloids are those 7 elements that make up the stair-step line on the periodic table, including boron and silicon. These elements have properties similar to both metals and nonmetals. Metalloids can take on either a positive or negative charge, depending on what other elements are around. These elements are particularly important for the electronic community. Nonmetals represent the top right of the periodic table. These elements are usually gases at room temperature and tend to form anions. Nonmetals have the highest electronegativity of any of the elements on the periodic table, meaning that they steal electrons from other elements. So, what are the halogens? The halogen family is the main group 7 on the periodic table, including fluorine down to astatine. They are all nonmetals, forming a singly charged anion. They represent all 3 states of matter. What are the halogens? The halogens are fluorine, chlorine, bromine, iodine, astatine, and tennessine. Not much is known about tennessine. The noble gases are the nonmetals that do not react with any element at all unless extreme conditions are imposed. They are the rightmost column on the periodic table. They usually do not form compounds as they have a full octet. They don't even bond with themselves. What are the noble gases? What do they consist of? Helium, neon, argon, krypton, xenon, radon, and oganesson are noble gases. With that, we have reached the end of today's topic, the periodic table. At this time, I want to remind all my lovely viewers to please subscribe, like, share, and hit that notifications bell. But before we leave, by the way, can you think of any elements that you use every day? Let me tell you, oxygen for respiration, nitrogen in the atmosphere, copper found in pennies, sodium and chlorine in table salt, hydrogen and oxygen that make up water that you drink, etc. Can you think of any more? Keep learning and keep growing with math and science concepts. Ciao!